Welcome back to G Fun Facts Online. Today, we are not looking at the stars or into the history books, but rather we are looking into the deep, dark, and churning waters of the Atlantic Ocean. We often think of the ocean as just a backdrop to our lives, a vast, blue, unchanging expanse. But it is not unchanging, it is alive. And right now, the Atlantic Ocean is showing symptoms of a heart condition. For thousands of years, a colossal, rhythmic pulse of warm, salty water has been pumping northward from the tropics. It is a planetary engine that moves more than 15 million cubic meters of water every single second. To put that in perspective, that dwarfs the flow of all the world's rivers combined. This circulation delivers the heat that keeps Europe from freezing, and it regulates rainfall patterns across half the globe. Scientists call this the Atlantic Meridional Overturning Circulation, or the AMOC, but you can just think of it as the heartbeat of the world. For decades, we have taken this heartbeat for granted. We viewed it as a constant, a guarantee of the stability we have enjoyed throughout the Holocene, the era of human civilization. But that is changing. In the quiet hum of supercomputers at Utrecht University, and in the frantic scribbles of oceanographers in Copenhagen, a terrifying consensus is emerging. The heartbeat is becoming irregular. The physics of the ocean suggests we are not merely facing a gradual slowdown, but that we are racing toward a cliff edge. In mathematics, this is known as a bifurcation point, a singularity where the current does not just weaken, but collapses entirely. Today, we are going to do a deep dive into the mechanics of this collapse, the physics behind the tipping point, and what it actually means for the future of our planet. To understand the collapse, we first must understand the machine itself. How does this engine work? The AMOC is often described in high school geography as a conveyor belt, but that is a bit of a simplification. It is more accurate to think of it as a massive heat pump. It operates on a principle of physics called thermohaline circulation. The word comes from thermo, meaning heat, and haline, meaning salt. These are the two fuels of the engine. The cylinders of this engine are located in the frigid, rough waters of the North Atlantic, specifically in the Labrador and Nordic seas. This is where the magic happens. Warm, salty water arrives here from the tropics via the Gulf Stream. When it hits the icy Arctic air, it cools down rapidly. Now, basic physics tells us that as water cools, it contracts and becomes denser. But there is a second factor. Because of evaporation in the subtropics on its way north, this water is already exceptionally salty. Salt makes water heavier. So, you have this unique combination of cold and salty water. When this water becomes denser than the deep water below it, it sinks. And it doesn't just drift down, it plunges. It sinks violently and voluminously, dropping 2 to 3 kilometers to the ocean floor. This sinking, known as deep water formation, is the piston stroke of the engine. It is the driving force. As that water sinks, it physically pulls more warm surface water northward to replace it. This suction sustains the current. The sunken water then flows slowly southward, along the abyss, hugging the ocean floor, eventually resurfacing thousands of years later in the Southern Ocean and the Pacific to complete the cycle. This circulation is the reason Liverpool, England, has mild winters, while Goose Bay, Canada, which is at the same latitude, is subarctic and frozen. The AMOC transports a staggering 1.25 petawatts of heat northward. To visualize that, it is equivalent to 50 times the energy consumption of the entire human species. That is the engine that keeps our climate stable. But here is the problem. This engine has a flaw. It is not a linear system. This is the most critical concept to understand today. You cannot simply turn the dial down by 10% and expect 10% cooling. The AMOC is a bistable system. This means it has two distinct equilibrium states. It has an on state, which is the strong circulation we have today, and it has an off state, where the circulation is weak or reversed, leading to a radically different global climate. This behavior was first described mathematically by the legendary oceanographer Henry Stommel way back in 1961. He created a simple theoretical framework known as the Stommel box model. Imagine two boxes of water. One is at the equator, representing warm, salty water. The other is at the pole, representing cold, fresh water. The circulation is essentially a battle between two opposing forces. First, you have thermal driving. The temperature difference tries to speed up the current. Cold water wants to sink, pulling the warm water north. But opposing this is the second force, haline braking. This comes from freshwater input, like rain and ice melt at the poles. Fresh water is light, it is buoyant, it refuses to sink. It tries to put the brakes on the sinking motion. In the on state, the current is fast enough to bring salty water from the tropics to the poles, faster than the rain, and melting ice can dilute it. The saltiness maintains the density, the sinking continues, and the current sustains itself. It is a self-reinforcing loop. Everything works. However, if you add too much fresh water to the North Atlantic, say from the rapidly melting Greenland ice sheet, the water becomes too light to sink. the current slows down. And this triggers a nightmare scenario known as the salt advection feedback. Here is how it works. As the current slows, it brings less salty water up from the tropics. Because less salt is arriving, the northern water becomes even fresher. Because it is fresher, it becomes lighter, and the current slows down even more. This brings up even less salt. It is a vicious cycle. Once this feedback loop dominates, the system doesn't just slow down gradually, it crashes. It crosses what mathematicians call a saddle node bifurcation. This is a point of no return, where the on state simply ceases to exist mathematically. The system must abruptly jump to the off state, and crucially, because of a phenomenon called hysteresis, you cannot simply reverse the process. This is the scary part. Even if we stopped global warming tomorrow, and even if the freshwater input from Greenland stopped completely, the current would not restart. Why? Because the salt transport required to kickstart the engine is gone. The off state is just as stable as the on state. We would be stuck in a broken climate. For years, this tipping point was theoretical. It was a ghost in the equations, something for modelers to debate. But in 2024 and 2025, observational data began to align with the theory in chilling ways. We are now seeing physical symptoms. The first symptom is something scientists call the cold blob, or the warming hole. If you look at a map of global temperature changes, the entire planet is overheating due to global warming. It is all red, except for one specific patch of ocean south of Greenland. That patch is cooling. This is not a fluke or a data error. It is the fingerprint of a slowing AMOC. As the conveyor belt slows down, it carries less heat north, leaving this specific patch of ocean colder than the rest. It is a direct, physical manifestation of the braking mechanism. But the most damning evidence came from a breakthrough study by researchers at Utrecht University in 2024. See, for decades, huge climate models had a positive bias. They were too stable. They predicted a slowdown, sure, but rarely a full collapse. The Utrecht team identified why. These models were not accounting correctly for the freshwater budget at the southern tip of Africa. They introduced a new physics-based early warning signal called the freshwater transport at 34 degrees south, or FOVS. Think of the Atlantic as a giant bathtub. The current flows in from the south and out the north. The key question is this: does the current import freshwater, or does it export it? If the AMOC imports freshwater, meaning the value is positive, the system is stable. If the current slows, it brings in less freshwater, making the Atlantic saltier and denser, which speeds the current back up. That is negative feedback, or self-correction. But if the AMOC exports fresh water, meaning the value is negative, the system is unstable. If the current slows, it exports less fresh water, leaving the Atlantic fresher. That reduces density and slows the current further. That is positive feedback. That is the runaway collapse. The Utrecht study confirmed that in the real world, unlike in those flawed models, the freshwater transport at 34 degrees south is negative. The Atlantic Meridional overturning circulation is currently acting as a salt importing mechanism. It is in the bistable tipping-prone regime. The study simulated this physics and found that once the tipping point is crossed, the collapse is not a centuries-long decline. It is a cliff. The breakdown occurs over mere decades. So what happens when the engine stops? The consequences are not limited to just a slightly colder London. The physics of the atmosphere and ocean are deeply intertwined. Let's look at the 4 major impacts. First, the European deep freeze. Without that 1.25 petawatts of heat, the temperature in northwestern Europe would plummet. Models predict a drop of 10 to 30 degrees Celsius in winter temperatures. London would acquire the climate of Svalbard in the high Arctic. Scandinavia would become largely uninhabitable. And remember, this cooling would occur despite global warming. The masking effect of the AMOC collapse would overpower the greenhouse effect locally. While the rest of the world burns, Europe would plunge into a localized ice age scenario. Second, we face dynamic sea level rise. The AMOC doesn't just move heat, it shapes the actual surface of the ocean. Due to the Earth's rotation, known as the Coriolis effect, the swift northward flow of the Gulf Stream pulls water away from the American east coast. It essentially leans the ocean against Europe. If the current stops, this slope collapses. Gravity takes over. The water would slosh back toward North America. The U.S. East Coast, from New York to Miami, would face a sudden dynamic sea level rise of up to half a meter to 1 meter. This is in addition to the rise from melting ice. Coastal cities would be inundated not by a storm, but by the physics of a stationary ocean. Third, the tropical rain belt would shift. The northern hemisphere would cool, while the southern hemisphere, no longer exporting its heat north, would warm. This is called the bipolar seesaw. This thermal imbalance would force the intertropical convergence zone, the rain belt that circles the planet, to shift southward. The consequences would be humanitarian disasters on an unprecedented scale. The West African monsoon would fail, causing total agricultural collapse in the Sahel. The Indian monsoon would weaken, threatening the food supply of over 1 billion people. The Amazon rainforest, deprived of its seasonal rains, would face a tipping point of its own, likely turning into a savanna and releasing massive amounts of carbon, further accelerating global warming. Fourth, and perhaps most haunting, is ocean anoxia. The deep ocean breathes through the AMOC. The sinking water carries oxygen from the surface down to the abyss. If the pump stops, the deep Atlantic loses its oxygen supply. This would trigger mass extinctions of deep-sea life. It could lead to the proliferation of anaerobic bacteria, which produce hydrogen sulfide. That is a gas toxic to marine life and humans alike. So, the big question remains, when? When will the cliff edge be reached? This is the subject of fierce scientific debate. Until recently, the Intergovernmental Panel on Climate Change stated that a full collapse before the year 2100 was very unlikely. However, recent statistical analyses have shattered this confidence. A controversial but statistically robust 2023 study by Peter and Suzanne Ditlevsen predicted a collapse could happen as early as 2025, with a central estimate around 2057. The Utrecht physics-based study did not give a specific year, but confirmed we are on course for tipping. It validated the statistical warnings with hard physical mechanisms. The distance to the tipping point depends on the rate of freshwater influx, and we know that Greenland is melting faster than expected. The scariest aspect of the physics of AMOC collapse is the silence before the noise. In a complex nonlinear system, the state often shows what is called critical slowing down before a bifurcation. The variability increases. The system wobbles like a spinning top losing momentum. We are seeing these wobbles now in the salinity data and the erratic behavior of the Gulf Stream. We are standing on the precipice of a planetary phase shift. We are not just changing the weather. We are breaking the engine that creates it. The physics is clear. The salt advection feedback loop is primed. The freshwater valve is open. And the warning lights, from the Southern Ocean to the North Atlantic, are blinking red. The question is no longer if the physics allows for a collapse, but when the accumulation of fresh water will finally overweight the scale, bringing the great Atlantic heat pump to a grinding, silent halt. That is the reality of the ocean's heartbeat. It is faint, it is irregular, and it needs our attention now. Thanks for listening to G Fun Facts Online.